All right, so this video is going to go over a couple of pages of our lecture notes and sort of explain what the heck that dice rolling thing was that we did in class. So what we did in class was we tossed a dice, right? A die. And the first experiment we did was to just toss the die 20 times and collect some data with other people and combine it. What we saw was a lot of variation. We expected to see if everything equally likely, but we saw a lot of variation. But if we could actually increase the number of times we had done that to 10,000, then you can start seeing that nice pattern we expected to see, a nice uniform distribution where everything is equally likely. Obviously, there's still some variation. It looks like our most likely outcome was rolling a 3, and our least likely was maybe this 1, but that's just due to random chance and the fact that even at 10,000, we're not going to get the exact correct distribution. We're going to have some variability there. Now, when we talked about the mean of the distribution, you guys calculated this both for the true distribution, and we could have actually gone and figured out what the mean of your simulated distribution was. And regardless, that mean should be right around 3.5, what we expect to see from half of our dice. Now, the next thing here is exactly what we did next in our worksheet. We talked about rolling a pair of dice and graphing the averages for each pair. And we see here exactly what we saw in that 3.5 was the most likely outcome because we roll a 7, 6 out of 36 different ways, 1/6 of the time, whereas something like 1 is less likely, right? This only happens 1 out of every 36 times because you'd have to roll a snake eyes to get 1 out. And so we can actually see that that's the least likely, and everything sort of has this trend. So the mean of this is still right around 3.5, right? That's the mode of our distribution, but we're starting to see something that is unimodal and symmetric. I believe this particular graph was made a little funky and that like this should be kind of cut into half like it is on the other side. I'm not sure what happened with the way they made it. I just stole it and have been using it for years and haven't really fixed it. If we start rolling even more die and taking their average, now we are a lot less spread out. As you can see here, it is very hard to get 1 or 6 because we need 20 die to come up a 1 to get 1. So that never happens. And even getting the numbers in the 2s is difficult because you need a lot of very low dice rolls out of the 20. So we still have a center of this thing at 3.5. That has not changed. But now we're starting to see still unimodal, still symmetric. But we're starting to see the big piece here, we're starting to see that bell shape, which means that normality is coming into play, and we'll probably be able to use our good friend the normal model to do a lot of stuff with our means. And then what we saw in class, as I asked you guys, what happens if we roll it 10 times and take the average? The biggest thing, besides the fact that it's becoming bell-shaped, is the fact that we're seeing less variation. I think that's what Cody said in the second class. It's less spread out. And this, remember, is the key to be able to do all of the stuff that we were doing in part 6. The idea that we got closer and closer to the real proportion as we continued to increase our sample size. So the same thing here, we're getting closer and closer to the real average of 3.5 that we expected as our sample size goes up. So we're going to use that and leverage it to make some statements about the mean in the end. So the first thing we have to do is figure out what that sampling distribution is officially. What are those calculations we could use? Part of that is we have a formal definition of what we saw in the dice rolling example, the central limit theorem. There are a couple of things I'll star as stuff I can ask kind of conceptual questions about. So understanding the central limit theorem in this sentence is important. It doesn't matter what the hell we start with in terms of a distribution. We could start with something I showed the second class, a bimodal distribution. And if we're looking at, if this is what our x follows, our x bar, as long as our sample size is big enough, will still become normal. It is not going to still have that 2 modes. It is going to have 1 mode centered at whatever the heck the mean of this distribution was, is where this thing will be centered. So that's what our central limit theorem says. And this only happens as long as n is big. Ooh, big enough. So that's the central limit theorem. We have some assumptions necessary to do all of this stuff, same ones we saw before when we talked about proportions. We still need independence. one person's outcome shouldn't influence the next. We still need our samples to be done using a simple random sample so we don't bring any sort of bias into our sampling. We still need our sample size to be small relative to the population, so we don't have to worry about that sort of idea that we're doing this without replacement. And now our rule of thumb has changed. Before it was NP and NQ have to be greater than or equal to 10. We no longer have a proportion, so we have to just use a standard cutoff for N, and that is 30. Now, we were already starting to see normality in our dice rolling example when our N was only 10. We were only rolling around 10 dice and taking their average. So that 30 is a conservative value, assuming you have like the grossest, most terrible distribution in the first place. 30 will overcome any grossness in your distribution. But if it's something symmetric, technically it doesn't really need to be this high. So that leaves us to our sampling distribution. We have a mean and a standard deviation. I'm sorry that those somehow got underlined. That's weird. This is in your formula sheet. So if we look at our formula sheet, we have this section here that says the mean and standard deviation of a sample mean. I have all this other crap written on here. So you have our mean and standard deviation there. So the mean of our sample mean, right? This says the mean of the sample mean. So if you took all your sample means and you average them, it will equal the true population mean. So if you grab a sample mean, really, it's going to come from this it's going to be somewhere around 3.5 with obviously some variation. And you can see the standard deviation here is the original standard deviation of our distribution divided by the square root of n. Because remember, as n increases, we have less spread. So that makes complete and utter sense that our n going up will make our spread or our standard deviation smaller. Second piece to this, besides just plugging into the formulas, which we're used to, is that there is now something we need to look out for. You guys have asked me a bunch in class, like, what is the difference between normal and approximate normal? Well, approximate normal means that it is only approximately normal, which happens when we start with something that's non-normal. So we started with our dice, we had a uniform distribution. In the example I drew with a bimodal, that's not normal. And in that case, the best we can say about our x-bar is that it is just approximately normal. But if we have something that is normal to start with, then we can finally use that big capital letter N that we've been ignoring up until now. So if we're told normal, we get normal. If we're told it's not normal, we get approximate normal. So we'll see this in an example moving forward. For now, I've sort of broken it down and introduced the topic, so I'll stop the video and I'll start the next one with an exercise.